Hello and welcome. This is Functions Review, including some graphs as well. I'm going to be just doing a bunch of example problems. Not much teaching about it, just saying how to do them. Let's start off. Got 3 problems to state the domain. Stating the domain means I must make sure that I find the values of x that I should or should not be able to plug in into an equation because I cannot get some outputs and have to figure out which cases they are. Like this one, I can't divide by 0. If x minus 4 was 0, that would be an issue. Add 4 to both sides, you will recognize that x could not equal 4. Okay. This one as well, I need to find something for which I'd be solving for x that would give me 0 and things that I have to avoid, things that would not give me values out for y. If x squared plus 1 cannot equal 0, subtract 1 from both sides, x squared could not equal negative 1. Take the square root of both sides, you say x can't equal the square root of negative 1. Now, the square root of negative 1 is not a real number. In fact, it's an imaginary number that's I. So if you had anything to put, it would be this. Otherwise, your domain is just all real numbers. In this case, I'm sure that you're more inclined to just put all real numbers because we're talking about points that we can graph, points that we can actually place on a number line. And in this case, or on a real number line. In this case, there's nothing there. But yes, square root of negative 1 is just this term I representing an imaginary number. So basically, no matter what I plug in for x, if you think about it, the smallest number you can get out of here is 0, right? So you take a number and you add 1 to it. There's no way you're going to be getting 0 out unless that was negative 1. And like I said, that won't really happen. Your domain is all real numbers. Finally, f of x equals 3 over square root of x squared minus 9. Once again, taking a look at that domain and saying, hey, can't make it 0. There's also something else, and I'm going to get to that in 1 second. But the square root of x squared minus 9 sure can equal 0. Okay? If I square both sides here, then I'll just get x squared minus 9 on the left, and I'll still have 0 on the right. So x squared minus 9 cannot equal 0. Add 9 to both sides, x squared cannot equal 9. And be very careful, you take the square root of both sides now, and you're saying that x couldn't equal positive or negative 3. If I put the in-between step, it looks like that. Absolute value of x cannot equal 3. Therefore, x cannot equal 3 or negative 3. Now, that's a certainty. That's one of my sets of values that I cannot put in. However, there's something else with this domain problem, and it says that this inside here, this is inside a square root here. Now, you cannot take the square root of a negative number for something that we were just talking about right here. So that's why I'm saying this one's kind of defunct, right? That's not really one that I'm referring to. I do not want to have negative numbers inside here, period. So we're only referring to the real numbers, but x squared minus 9 has to for sure be 0 or larger. Okay? So x squared has to be greater than or equal to 9, and take the square root of both sides. And just think about what kinds of values for x you can plug in when this is happening. If I square the number negative 5, would that be an issue? No, because you square negative 5 and you get positive 25. So think about the values of x that you can be. You can be greater than or equal to 3. This is taking the square root of both sides. You can be greater than or equal to 3, or you can be less than or equal to negative 3. And something that might help is me writing that in-between step one more time. This one, absolute value of x is greater than or equal to 3, because this now breaks off into this idea right here. So x can be greater than or equal to 3 or less than or equal to negative 3. Now, I have to conjoin both of these sets in this domain, and anything that can't be included in one means it can't be included in the other as a whole. So it says here, x can be greater than or equal to 3 or less than or equal to negative 3, but here it says x can't equal 3 or negative 3. Because if I did put it in 3 or negative 3, I'd be taking the square root of 0, which is okay, but then I'd be dividing by 0, which is not okay. So my final solution set is x can be greater than 3, or x can be less than negative 3. I can't really have 3 or negative 3 be a part of my values. And there is my domain. If I want to do interval notation for any of these, interval notation is more about the values that it can be only. So if you can't be negative 4, that means you can be anything but negative 4. So there is a left interval where I can go from negative infinity to negative 4, not including negative 4. And unionizing it with this one, I could also be anything from -4 to positive infinity, not including -4. Remember, these parentheses here indicate that it can't be it. If they were square brackets, it means you could. In this case, I cannot be -4. So there's another way of expressing the domain for number 1. For number 2, another way of expressing this domain for all real numbers, saying you can go from -infinity to positive infinity. Not including those as well. We can never really include negative or positive infinity when mentioning that. And number 3, if this was the answer, which I know it's not, I'm just showing that I can do some square brackets, I could go from apparently -infinity to -3, not including including -3 in this case, and also including +3 and going to positive infinity, like so. Of course, we know that's not the case. The final answer really is this one, where you cannot equal 3 or -3. These should be parentheses and not square brackets. Notice that the values it can't be are anything between -3 and 0. And finally, if I wanted to graph these on a number line, they would look like this. This one's actually going to be kind of weird looking because the only thing you can't be for x is -4. So you can be everything else one way or the other. We wouldn't often graph those ones. This second one is also weird as well, number 2, because there are no restrictions. X can be anything. So that just means go forever left and right like that, and that would be x. You don't have to put a solid circle anywhere. I guess if you wanted to right there, there's no problem. But yeah, it's not necessarily an issue. And then this last one is where it makes the most sense to kind of have a number line to graph this with. That here's 0, here's 3, here's -3. Cannot include these, so open circle goes to the left, and open circle goes to the right. Whoops. There you are. So domain's all about the values of x that would give you issues. For the most part, what we're looking at not doing is not dividing by 0 and not taking square roots of negative numbers, something like that. All right, are these functions even, odd, or neither? If a function was odd, it would be symmetrical with the y-axis. Excuse me, with the origin. If it was even, it would be symmetrical with the y-axis. And if it's neither, it's symmetrical with neither. Now, this function is odd-powered, and odd-powered functions are impossible to be even functions. So that's not even one I'm going to consider. So for an odd-powered function, what I'm looking for is I'm going to plug in a couple x, y values, and then I'm trying to make sure that I can get something that is symmetrical with it, meaning it would have a point that is -x, -y. So as I substitute some values, let's see if that's what I end up getting out. So here we go. First one I'm going to try is 0, 0. I need plugging in 0 for x, because I need 0 for y for this to be an odd function. It needs to be symmetrical with the origin. So 0 cubed minus 0 is 0, so that one works out just fine. So far, so good. Next one, if I substitute 1, 1 cubed minus 1 is 0. Now, if I substitute -1, I better get 0 out as well. -1 cubed is -1, minus -1 is plus 1, so -1 plus 1 is also 0. Also, so far so good. Probably at least try one more set, right? Try it until it's wrong or until you feel convinced enough. How about 2 and -2? So if I plug in 2, I get a value. It's 8 minus 2, which is 6. I plug in -2, I better get -6. -8 minus -2 is -8 plus 2. That's -6. So it looks like things are working out here. Anything that I plug that's an x, y value, I'm also getting a -x, -y back out, even the zeros. So I'm going to trust this thing. This looks like it's an odd function. Number 5 here, h of x equals x squared plus 1. It's impossible for this one to be an odd function, so this one could only possibly be an even function. And this is something that, I could prove without actually doing a table, because I could graph this. I could actually graph both of these next two ones. I'll do that thereafter. But here, I shouldn't be substituting 0 necessarily. I don't have to get 0, 0. But I should try my 1, -1, my 2, and my -2, etc. Maybe 3 and -3. But for this one right here, any x, y value I choose, I better get a negative x comma y value out for. So x, y, and negative x, y would be the symmetry. This is reflecting across the y-axis. So I plug in 1. 1 squared is 1 plus 1 is 2. Now when I plug in negative 1, I better get positive 2 back out as well to be the same height. Negative 1 quantity squared is 1 plus 1 is 2. Good. 2 squared is 4 plus 1 is 5. Negative 2 squared is 4 plus 1 is 5. So you can see what happens if I square my value, then it just becomes the positive version of itself. So even 3 squared and negative 3 squared give you both 9, plus 1 is 10 each. So you can see how I'm getting the same matching value out. That's good. That does make this an even function. To prove it through the look, and you might know what this looks like before you actually graph it, but let's say I did graph this thing. All I'm looking to do is, this is kind of in vertex form here. My vertex is at 0, 1. My stretch factor is 1, so I go over 1 up 1, over 2 up 4, and over 3 up 9. Here, left side, over 1 up 1, over 2 up 4, over 3 up 9. And its symmetry, as you can tell, is with the y-axis. All parabolas, all quadratics are symmetrical, but not all of them are with the y-axis. This one happens to have its vertex at the origin. And maybe that's something else that you can try and find too. If you can figure out your vertex is at the origin, in other words, there's no b term here, it's 0x, then you've also kind of proven your point. Number 6, I could also graph with as well and prove that it is actually going to be neither. But what you're going to do here, once again, is another test. And I can test this one really quickly. Remember, this can only be an odd function. It couldn't be an even function because it's odd powered, which means I should test the point 0 and see if I get 0 out. 0 cubed minus 1 is a negative 1. Already, I know it's neither. It must be symmetrical with the origin for it to happen, and there's only one y value when x is 0, and that's negative 1. And once again, to kind of prove it, besides just that one point, let's plot a few more points here, just like I would a cubic. So, going over, sorry about that, 5, 6, 7, 8, sure. So there's one point at 0, negative 1. That is the starting point. Once again, from there, you can already tell it's an issue. You go over 1, up 1 cubed, over 2, up 2 cubed, which is right there. Down, left 1, down 1 cubed, left 2, down 2 cubed, like that. So this cubic graph ends up looking kind of like that, curves. And you can see it's not symmetrical with the origin. It's not reflecting across the origin. It doesn't have 180 degrees of rotational symmetry about the origin. It does right here. And there's a difference between the two. Number 3, given f of x equals x squared plus 1 and g of x equals x minus 4, let's find the following. F times g of x, f of g of 2, and f over g of t, stating the domain on that one. So number 7, f times g of x can be also written as f of x times g of x, which is x squared plus 1 times x minus 4. So I have to kind of distribute everything here. X squared times x is x cubed. X squared times negative 4 is negative 4x squared. X times 1 is x, and 1 times negative 4 is negative 4. And that's what that thing expands out to be. So if I took f times g of 7, I could plug 7 just into here instead of into there. No biggie. Number 8, f of g of 2. Okay, I can do this one of two ways as well. One way is I could just go ahead and do f of g of 2, which literally means like so. Take g of 2 first, and whatever output I get, I'll take f of that. So that becomes f of 2 minus 4, f of 2 minus 4, okay? Because 2 goes into there, so it's f of negative 2. I'm going to take negative 2 and substitute it into here, so that becomes negative 2 quantity squared plus 1, which is 5. So f of g of 2 is 5. A second way of doing this is taking the f of g of x first, figuring out what f of g of x actually is, and then substituting 2 into that expression. So one thing I can do here is I can take f of g of x first, Okay? And that'll become f of x minus 4. And I put x minus 4 in place of x right here. So that'll become x squared, x minus 4 squared, I think plus 1. Yeah, plus 1. And I could keep going. I could keep expanding this thing. In fact, I will. But once you kind of have something there, you can also substitute 2 in. I suppose you'll be doing the same stuff there, though. So let's just clean this up. X squared minus 8x plus 16, then plus 1, which becomes x squared minus 8x plus 17. Substitute 2 into here now, because this is f of g of x. Now f of g of 2 will become 2 squared minus 8 times 2 plus 17. Okay, and that becomes 4 minus 16 plus 17. And please don't do 16 plus 17 first here. 4 minus 16 first. Or you can do negative 16 plus 17, but make sure you don't do just 16 plus 17. 4 minus 16 is negative 12, plus 17 is 5. And you can see that we also got 5 up there. This one looks like it took significantly longer, and you might be wondering why it is we'd ever do that. It depends on the problem. Sometimes it'll go a lot more quickly with that, or if you have a lot of things to input, sometimes that would be the best route. In this case, it didn't really seem like it. But it's all right. You have another method. Finally, f over g of t, and state the domain. Okay, f over g of t is f of t over g of t. And what we'll do is we'll substitute t in for x, that's all. And we have t squared plus 1 for f of t over t minus 4 for g of t. And nothing else can cancel. That's it. I can't factor t squared plus 1. These t's can't cancel out. You're good. You're set. But stating the domain here, you also have to state that t cannot equal 4. For the same reason as we did for problems 1, 2, and 3, you cannot substitute 4 into here and divide by 0. That would be an issue. And there's your domain. Okay, inverse functions. If f of x equals 2x cubed minus 5, let's find the inverse function of x here. So first things first, let's put y in place of f of x to just make sure I can recalculate some things here, maneuver that y around. It's easier to work with. I'm going to go ahead and swap y with x on this next step here, because this equation here represents the inverse immediately. But we have to make sure that y equals whatever here so we can substitute this in its place. So let's keep working with this problem. Solve for y. I'm going to move this 2y cubed over to this side. Just simply move it. And move the x over to that side. Add 5 to both sides. Right there. Divide both sides by 2. Y cubed equals x plus 5 all over 2. And finally take the cube root of both sides. So this will say, one second. Cube root of both sides here. We get y equals the cube root of x plus 5 all over 2. Now, some might argue that we have to have a rational denominator because technically this is irrational. Right now we're looking at this right here. Okay, cube root of 2 is in the denominator. So what you might do is you might multiply both sides, or top and bottom, by the cube root of 2 over the cube root of 2 twice. Okay, you'd have to do this twice to rationalize it because it's cube root, not square root. Another way of putting that, this is the cube root of 4. So we can multiply top and bottom by the cube root of 4 over the cube root of 4. I'm only stating this in case you get another value for, let's say someone else does it, answer key, whatever it is you're working on. Here, the cube root of 4, the 4 can distribute in with this x plus 5, and you'll get the cube root of 4x plus 20. On the bottom, you'll have the cube root of 8, because that's the cube root of 4 times the cube root of 2. And the cube root of 8 is 2, so this is the cube root of 4x plus 20 all over 2, like so. So that is the most appropriate answer when it comes to the end. Otherwise, that one's okay. You get to there. But here, this is inverse function, completely simplified. There you are. That's it. That's the only inverse function we had to find. Okay, is the function f of x equals 3x minus 2 over 5 1-to-1? What they're asking you is, does this equation generate an inverse that is also a function. Meaning, here if I substitute any value for x, I'll only get one value for f of x or for y. If I took the inverse and substituted in values for x, would I also only get one value of y each time as well? So, how do you know this without taking the inverse? You might have to know what kind of problem type this is. This thing, without setting up a table even, this guy can also be rewritten as f of x equals 3/5 x minus 2/5. Now, why does that help me? Because I know this is y equals mx plus b. I know this thing's linear. Linear, no domain issues as well. I'm getting all real numbers. The point is, in order to figure out whether or not the function, without finding the function first, in order to figure out whether or not this function will have an inverse that's also a function, we can do something called the horizontal line test. And the vertical line test would be for the original function to see if this thing is a function. It looks like it is. The horizontal line test is for the inverse, because if I took the inverse, it would have to pass its vertical line test. And the inverse of a vertical line, of course, is a horizontal line. This passes the horizontal line test, and the horizontal line test says that I'm only passing through one value for x for every value of y that I'm choosing here, no matter what I choose there. So, as it passes it, this must be a function. Yes, it is. So let's find its inverse. Now, I know its inverse is going to reflect across this line right here, so it's going to look something like this right here, except probably without the dotted line. Let's make it an arrow like the other one. Okay, it's probably going to look something like that. So let's see what we end up getting as a result of this. So y equals 3/5 x minus 2/5. You know, it's probably easier to write the original one, actually. Y equals 3x minus 2 all over 5. Swap x and y here. We're going to get x equals 3y minus 2 all over 5. Solve for y. Multiply both sides by 5. Okay, we'll get 3y minus 2 equals 5x. Add 2 to both sides. 3y equals 5x plus 2. Divide both sides by 3. Y equals 5x plus 2 all over 3. Or I can also write it in slope-intercept form, which would say 5/3 x plus 2/3. So let's see if that kind of at least looks like the green graph up here I was referring to. Plus 2/3 means the y-intercept's above 0. And then 5/3 up 5 over 3. It's got to be steeper than that one. And the other reason I said it should look like that graph, tilt your head 45 degrees to the side. Looks like these kind of reflect across here. Of course, I had a rough sketch, but they definitely should intersect at some point down there, whatever that is. They should meet up. Yes, there's an inverse. That's what it is. And all of these have inverses. I think the question was, you know, not an inverse function. There's a difference between an inverse of a function and an inverse function, I suppose. This one very specifically is also a function. Other ones that we draw might not be functions, but that doesn't mean we shouldn't be taking its inverse at times either. Determine algebraically that f and g are inverse functions. So there are a couple ways we can go about this. I'm basically just going to take f of x and take its inverse. Then I'll take g of x and take its, I can't say this. I'll take g of x and take its inverse. And finally, I'll take f of g of x and g of f of x and show that I get x out. So 4 different ways you could show how to do this. And I'll go through all of them very quickly. Start there, swap x and y, solve for y. And when I solve for y, I better get this back out. So subtract 5, take the cube root of both sides, cube root of x minus 5. So the inverse function of x is cube root of x minus 5. That matches with g of x. So far, so good. Let's go ahead and star it. There's one way. Second way is with g of x over here. Go ahead and place y in for g of x. Swap x and y. This will be the inverse. And we'll solve for y. Cube both sides here. So this will be this cubed and this cubed. We'll get y minus 5 equals x cubed. Add 5, you'll get y equals x cubed plus 5. Or right there, x cubed plus 5, which matches with f of x. Okay, those are two ways. The last two ways I was talking about, it's the same idea, but taking f of g of x, okay, and g of f of x. The reason I'm saying this is because if you take f of the inverse function, of x, I should be getting x, and same with g. G of the inverse function of x, I should also be getting x. Okay, so if I have that there, let's go ahead and try and take these inverse functions and see if that's what we get out here. All right. Now, of course, it should work because I already showed it this way, but let's just, let's keep working it out. So f of g of x, let's use blue, will be f of g of x like so. So that becomes f of cube root of x minus 5. Now I'm going to take cube root of x minus 5 and place it into here. So that becomes the cube root of x minus 5 quantity cubed plus 5. Cube root of x minus 5 quantity cubed is x minus 5. Plus 5, these cancel out, you're left with x. So it shows that if I get x out, then these are inverses. That's actually true. That's a true thing to check for. Same with this, because what I'm inputting is what I'm also getting for an output. So if I got the output back out, that's good. It reflects it across y equals x twice, essentially. G of f of x is also written as g of f of x, which is g of x cubed plus 5, which is the cube root of x cubed plus 5 minus 5. This is taking place of x, which is the cube root of x plus 5 minus 5. The negative 5 and positive 5 cancel out. You're left with x cubed. Cube root of x cubed is also x. So let me add stars to these things because I want to as I wrap this up. 4 different ways to determine that they are inverses. A fifth way would be to graph them. But I guess they did ask to do and find out and look and see that they're reflections, or plot them in a table and see that the x and y values switch. But it did say algebraically, not graphically, so there are other ways to do it, but these are 4 conventional ways to do it algebraically. Number 13 is y plus 2x equals 3 a function, y squared minus 3x equals 5 a function, x squared plus y minus 5 equals 0 a function. Let's do these one at a time. I'll start with this one. For it to be a function, they do mean literally is y a function of x. Okay, because x might be a function of y, but we're referring to y as our dependent variable and x is our independent variable here. At least make that assumption. So solve for y, you get y equals negative 2x plus 3. Negative 2x plus 3, this linear equation, yeah, that's definitely a function. When you're going to refer to something that's not a function, it's going to be something in the sense that you'll probably get a plus or minus in the equation, something that would fail the vertical line test, something that would look like a circle, something, a sideways parabola, anything like that. All right, this one right here, let's change colors. This one right here, is this guy a function? Well, y squared equals 3x plus 5. Take the square root of both sides. Y equals plus or minus square root of 3x plus 5. You can see here's where we're getting one of those issues. This is a graph that has some sort of, I don't know the exact look, but has something like that going on. Failing the vertical line test because here's plus root 3x plus 5. Here's minus root 3x plus 5. No, this one's not a function. It's failing its vertical line test. And final one right here is x squared plus y minus 5 equals 0 function. Subtract x squared from both sides. Add 5 to both sides. Y equals negative x squared plus 5. This is a downward facing parabola. Something like this right here. Symmetrical with the y-axis actually. It's passing the vertical line test. Yes, this one is a function. However, its inverse would not be. This guy's inverse would not be a function here. And I don't think we had to find domain and range, but if you were curious, the green's domain and range are both all real numbers. for that linear equation. For this square root non-function, for this guy here, your domain, you have to figure out that this guy has to be greater than or equal to 0. 3x plus 5 is greater than or equal to 0. 3x is greater than or equal to negative 5. Therefore, x is greater than or equal to negative 5/3. That would be your domain here. Anything less than that number, you'll be getting negative values. The range in this case is actually all real numbers. You can see that from the graph right here. This thing would go on forever upward and forever downward, and that one's kind of an issue for this particular problem. And finally, this last one here, domain is all real numbers. Once again, you could put in anything there. There's no issues there. Range, you can kind of see where there are issues. Once you find your vertex, you've peaked, you've topped out. And this top one, like I said, the vertex is at 0, comma, in this case 5. So anything less than or equal to 5 would be the range there for the y values. These are not in interval notation. I apologize for not putting them in that, but this wasn't even asked for you for this one anyway. Anyway, range is a lot easier if you draw the graph out, if you find something with it. Seeing it just through the equation is kind of difficult to do. Number 14, what is the domain and range of f of x equals square root of x plus 2? Okay, here's why domain and range matter. Domain, once again, you're considering the fact that you're inside the square root has to be greater than or equal to 0. It cannot be negative. Therefore, x must be greater than or equal to negative 2. Okay. Your range, a lot of different ways you can do it. I mentioned graphing it, like using a table. But let's say you didn't use a table, or let's say you wanted a different way of knowing it. You kind of have to know something about the function. This is a square root function. And square root functions have the knack of starting at some point and either going that way, or going that way, or going that way, or going that way. In other words, whatever point it starts at, it automatically goes to its left or right and up or down. Now, left or right doesn't really matter in this case, but it sort of does. I have to go to the right. That's for domain. But range is saying I can either go all the way up or all the way down from my left or rightmost value. This negative 2 is really crucial for this particular problem. Here's negative 2 right there for x. When I plug in negative 2, I get 0 for y. This vertex form of this thing would say I start at negative 2, 0. And everything goes to the right. And the question is, from here, does it go up or does it go down? Well, this is based on whether or not your square root function is positive or negative. It's positive, so it's going to be going up. And it's going to be going up from here. It's going to be going up forevermore. You can never get any negative values out from here. Remember, when you plug in a negative value, you can't take the square root of a negative anyway. Everything for y is going to be 0 or greater than or equal to. You could plot a couple points and recognize that, or if you know enough about that particular problem, you could find that in a matter of seconds, literally. Didn't have to go through my whole explanation, just the understanding of how you're finding that. So there's domain and range. Let me go ahead and do one set of interval notation for you, because I haven't done it in a while now. Domain, I can go from negative 2 to positive infinity. It includes negative 2. Range, I can go from 0 to positive infinity, and that includes 0. There you are. Number 15, graph y equals negative 2 times the absolute value of x minus 3 plus 1. Write the domain and range. Okay, your stretch factor is negative 2. This will be a downward facing, vertically stretched absolute value function, which is a V shape. So here's the parent graph. Our graph is going to look more like that, downward. And I'm going to start at my HK value. My vertex will be 3, 1. When I substitute 3 for x, I get 1 for y, because all this goes away. So starting at 3, 1 here, every time I go over 1, I should be going up the absolute value of 1. But I got to take that 1 that I go up, multiply it by a negative 2. 1 times negative 2 is negative 2. I'll be going down 2 instead. Go over 2 instead of going up the absolute value of 2, which is 2. 2 times negative 2 is negative 4. So instead I'll be going down 4, like so. 3 times the absolute value, or 3 over 3 up the absolute value of 3 times negative 2 is negative 6, going down 6. And this is linear. It's a V shape. You can see that it kind of has a down 2 over 1 slope going for it. And this would continue in this path for absolute value of 4 and 5. Now, it does not go up this way. It's not completely linear. No, this is a vertex right here. it's V-shaped. It has a bounce on the other side. Or if I went left 1, I'd ordinarily be going up the absolute value of negative 1, which is positive 1, but multiply that by negative 2, I'll be going down 2 here as well. These will be reflecting across here, like so. Same distance away, 4 away, 4 away, 5 away, 5 away. Okay, maybe not that many points are necessary, but it's complete enough. And I know absolutely what I'm doing with it, so no harm, no foul, right? V-shape, downward, more stretched than just a stretch factor of 1. Domain. You can either put all real numbers or an interval notation. It'd go from negative infinity to positive infinity. There are no issues there. Range. What's the highest this thing goes? You can see it from the graph. The highest it goes is 1, and it only goes downward from there. Y can be less than or equal to positive 1. Or you may put it goes all the way from negative infinity, as low as that, up to positive 1, including positive 1. I'll put or to state I can do one or the other. Number 16, f of x equals negative square root of x plus 3, right domain and range. Okay, this in the more detailed vertex form, it would look like this, as to state that my stretch factor here is negative 1. And the starting value, I want to call it a vertex, not really sure if I should be calling that, is negative 3, 0. I substitute negative 3 in for x, I get 0 inside here, my y value becomes 0. This is my leftmost, or starting point. Now, we just talked about a square root graph a little bit ago. If this negative exists outside here, the stretch factor of negative 1, we know it will be flipped over. So what should normally look like this will end up going downward this way. Let's find out what some exact points are. If I displace myself 1 away from this vertex here, I should be going up the square root of 1. But I got to take that and multiply by negative 1. Up the square root of 1 times negative 1 is negative 1. Going down 1. Going over 2, I'd be going up the square root of 2. Don't really want to do that. Going over 3, going up the square root of 3. Don't really want to do that. Going over 4, up the square root of 4. I'll do that. That's 2. 2 times negative 1 is negative 2. So instead of going up 2, I'll be going down 2. 5, no. Square root of 6, no. Square root of 7, no. 8, no. 9, okay. Up the square root of 9 is 3 times negative 1. Instead of going up 3, I'll be going down 3. And so on and so forth. Multiply your stretch factor after you apply the behavior of your function, and you're good to go there. Domain. X has to be greater than or equal to negative 3. We could have established that early on right here, where you say x plus 3 has to be greater than or equal to 0. Subtract 3. You will now say x is greater than or equal to negative 3. You can also see that in the graph here. Range, which of course is limited by the domain, and this leftmost value indicates the top or bottom of your range. In this case, it's the top. Y can be 0 or anything below it. So y is less than or equal to 0. In interval notation, for x is greater than negative or equal to negative 3, its leftmost bound is negative 3 and goes up to positive infinity. Range here, your y values can go from 0 or down below. So goes from negative infinity all the way up to positive, or not positive 0, all the way up to 0, including 0 right there. Number 17, graph another square root here. Now this one's a little different. I haven't done a lot of these with any video yet. Maybe I've done one of them. Let me write this in kind of a different light here. There's a 1 here. Whoops, that's kind of bad looking. There's a 1 on the outside. Inside the square root here, I'm going to factor a negative 1 out of here for a moment, because it's really about saying I want x to be positive if possible. That would really be helpful for me to figure out if x was positive or not. Some people might not like this look, but if you do have this value outside of here, make it either a 1 or negative 1. If there's any other value, please get it outside of the square root. That's kind of a topic of conversation that would be something else. This guy indicates right here that you will be going to the left instead of the right. The other thing you don't want to confuse yourself with, although you should be doing it a better way anyway, is Don't think that you're starting at negative 3, 0 like this just because this is a positive 3. It's asking what value of x do you put in for this thing to become 0 inside here. The answer is a positive 3, not a negative 3. Likewise, you can see that it's going to be the opposite in this sense. So one way or the other, you should be able to find that. Now, another way of knowing this goes to the left is just by writing the domain first. You can realize that negative x plus 3 has to be greater than or equal to 0. If I subtract 3, negative x has to be greater than or equal to negative 3. Divide both sides by negative 1 or multiply both sides by negative 1. The inequality flips. X has to be less than or equal to 3, as you can see. So less than means to the left of. This would be your starting point here at 3, 0, like I said. This thing indicates we go to the left instead of the right. Everything else is going to be the same with the exception of that. So I'm not going to be going one to the right and going up or down. I'll just be going one to the left with the same idea. If I go one to the left here, I'll be going up the square root of 1. My stretch factor is 1, so I don't have to worry about anything else. If I go 4 over, I'll be going up the square root of 4, which is 2. And 9 over, I'll be going up the square root of 9, which is 3. Etc., etc. Whoa. Here we go. Not too bad. That is terrible. Anyway, square root graph going that way. So I did already state the domain. It was x is less than or equal to negative 3. In interval notation, I can go from negative infinity to, sorry, not negative 3, positive 3. I can go from negative infinity to positive 3, including positive 3 there. Range, as you can tell, y would be greater than or equal to 0, given everything here. Positive stretch factor, starting at 3, 0. My range, y is greater than or equal to 0. So that goes from 0 to positive infinity, like so. Number 18, describe the transformations that will yield the graph of g of x equals negative 3 times x minus 4 plus 6. So first thing is I'm going to just go ahead and give you the parent graph here. F of x equals the absolute value of x, just to indicate we're doing our transformations based on this. Okay, based on this one right here, what different transformations take place. Now you might be able to just state them. That's okay as well. But let's look at the two graphs and see what's different. This one here has a vertex at 4, 6, has a stretch factor of negative 3. Let's change this color. So in graphing this guy, starting at 4, 6, right there, if I go over 1 instead of going up 1, multiply that by negative 3, I should be going down 3. Over 2 instead of going up 2, remember this is absolute value, up the absolute value of 2. Multiplied by negative 3, I'll be going down 6, and so on and so forth. This is constant, kind of like a slope of negative 3 over 1, only like I said last time, this has a vertex, so it bounces over on this side, and we have this look. Okay. Now, they did not ask you to graph necessarily, but using this graph might help indicate the different things that happen here, although we indicated them when we graphed them as well. So, what are the things that occurred? There was a shift. Okay, I could have taken this graph here, and I could have said, hey, let's go ahead and shift this 4 units to the right and 6 units up. Okay, shift 4 units to the right, 6 units up. Then, this also, and I can't really do it right from here because oh yeah, I can. Then we flip it upside down. Okay, so it goes downward. That's what the negative's doing. Flip over. And then we stretch it. Stretch vertically 3 times. So you see how these points go over 1, down 1. This goes over 1, down 3. Over 2, down 2. Over 2, down 6. So we got to stretch this vertically 3 times larger than the other guy here. Now, I can't really do that apparently, so forgive that. But anyway, it stretches, it changes more to that one. It morphs into that. There. So those are the 3 things that you should describe there with those 3 transformations given this exact one. So taking this parent graph, that's what you do. Take an absolute value graph and do those to it. Number 19, write the equation for the graphs. Okay, so just like the last problem there, it's good if you know the information that you're dealing with here. First one is, this is a quadratic equation. Okay, so the original parent graph was y equals x squared. Okay, what we're trying to find is something else that says y equals a times x minus h squared plus k. So we need to find a, h, and k here. H and k refers to the vertex point right here. That's -2 comma +2. So far we know this should say y equals a times x minus -2 quantity squared plus 2. Also, this thing's flipped over, so you know that your a value is negative. This one goes over 1, down 1, over 2, down 4, possibly over 3, down 9. I think we can assume that. This stretch factor is -1 here. It's not taller or shorter than just going x squared. Over 1 up 1, over 2 up 4, over 3 up 9. So the a value is -1, so your final equation based on this is y equals -1 times x plus 2 quantity squared plus 2. A lot of people won't put the -1, at least answers normally wouldn't. So you can just put the negative right there. You'd be good to go. Flipped over, shifted 2 units to the left, 2 units up, no other stretch factor in place. So that was A, actually. I should write down the letters for this one. The red one's B and the green one's C. Okay. One sec. Okay, B right here. And somewhat apologies for not extending this out farther. This actually starts right here, and it keeps going out that way. Okay. It's actually crossing events somewhere there, if that matters. But you might already know a little bit of things about this one. This one's a little more tricky, though, because, like I said, I haven't done a lot of problems with square root graphs going to the left. But if they do, first of all, we know it's a square root graph. So we want this form. Now, when I write this form, I'm going to write a b inside here. B for us is either going to be 1 or -1. If it's a positive 1, then it's irrelevant. If it's a -1, then it's going to the left. So here, our b value is -1 because this thing goes to the left. Okay, much like this problem before it, not that one, much like this problem before it right here, that -1 means it goes to the left. I factored it out of in there. Okay, that's first thing. Square root graph, it's at -2, -2. That's where we're starting at. And its stretch factor, it's positive, and it appears just to be 1. You go over 1, up the square root of 1. Over 4, up the square root of 4, which is 2. That's where that other one goes as well. So A is just a positive 1, and your H is -2, and your K is -2. So your final equation for this one is going to be y equals 1 times -1 times x minus -2, that's x plus 2, minus 2 right there. Kind of difficult one to deal with there. The 1 outside can essentially disappear. You can distribute this -1 into the -x and the -2, like so, and it looks like that. Kind of confusing looking problem with everything there. This is for part B, once again. No, yeah, that's it. Finally, part C, also a square root graph in its own right. It's going this way here. Going downward, you can see the points it's hitting through. Kind of same kind of look. It's got a stretch factor of 1. Actually, in this case, the stretch factor is -1. You can see it's flipped over, so you know your stretch factor is negative. Over 1, down the square root of 1. Over 4, down the square root of 4. You can see where that's coming into play. It's starting at 1, 2, so your H is 1 and your K is 2. There's no B value to worry about here. Your B value is a positive 1. It's not going to affect anything there. So this is just better written as y equals -1 times the square root of x minus 1 plus 2. Okay, flipped upside down helps with that. Knowing your stretch factors and how those things work, these were all regular stretch factors. Anticipate that you won't get anything too drastic or scary, especially fraction stretch factors. That would be a big issue. Number 20, sketch f of x equals x squared plus 1 and its inverse on the same graph. So let's go ahead and sketch x squared plus 1. I think I actually sketched x squared plus 1 once. I think a problem was involving that. This one starts at 0, 0. This is also better written as 1 times x minus 0 quantity squared plus 1. So your vertex is at 0, 1. Your stretch factor is 1. Starting at 0, 1, over 1 up 1 squared, over 2 up 2 squared, over 3 up 3 squared. Reflect across your vertex. Boom, boom, boom. There is x squared plus 1. Not bad looking, not bad looking. Maybe I spoke too soon. That looks okay. Okay, draw its inverse. So there are a couple ways we can go about this thing. One is calculating the inverse and then graphing it, which I will do, but not just yet. Another way is also going against y equals x right here. So I'll go ahead and do the equation first, but I'll also show you how to do the reflections here. One way is just using a table, and that's probably how I'm going to end up doing it. Okay, it's inverse. It's inverse right here. Let's go ahead. Y equals x squared plus 1. Swap x and y. Here is going to be its inverse graph, y squared plus 1. Which, like I said, you can always use a table, plug in values for y, get values out for x. But let's go ahead and solve this one. X minus 1, y equals plus or minus the square root of x minus 1. Now, plus or minus is important, which means it's split into two separate equations here. There's positive square root of x minus 1, and there's negative square root of x minus 1. Now, it's kind of bad to say this because this is not actually a function. But these are two different graphs we got to graph here. So both of these start at the same place. They start at 1, 0. And they both have a stretch factor. Well, one's a stretch factor of 1, one's a stretch factor of negative 1, which means we'll be going up and down the same amount depending on how much we go over. So we start at 1, 0. For the positive one, if I go over 1, I'll go up the square root of 1. Over 4, up the square root of 4. And over 9, up the square root of 9, right there. The negative one, if I go over 1, I'll be going down the square root of 1. Over 4, down to the square root of 4. And over 9, down the square root of 9. You can see how this graph kind of correlates with the other one that we were just doing regarding the points that they have. And that makes sense because this is an inverse graph. Inverse of the function, even if its inverse is not a function. So you can see why it's still sometimes important to be able to take its inverse there. Another thing I can mention and keep in mind and see if it actually worked out, the domain for my original function was all real numbers. The range was y is greater than or equal to positive 1. Okay, for my inverse right here, my domain is x is greater than or equal to 1, and my range is all real numbers. And that should be happening. My domain should become my range, and my range should become my domain for these two, except for swapping x and y. But in interval notation, it should look the exact same. So another way we can go about this problem there to graph its inverse is if you know how to graph y equals x squared there, whether or not you used a table, you can do some swappage now. So what I'm going to do are 1, 2, 3. I need to plot some more points here. Sorry, it's not the best line work here. I'm going to go ahead and actually copy and paste this thing over. I'll make two different tables. Excuse me. You may move. Thank you. Let's go ahead and do two tables here. One is with original function, one is with inverse function. Okay. Okay, so for x and y for the original function here, when I had plugged in 0, I got 1. When I plugged in 1 and negative 1, I got 2. When I plugged in 2 and negative 2, I got 5. And when I plugged in 3 and negative 3, I got 10. Now, what you can do if you didn't have this graph yet, right? I could take the y values and turn them into x values. But I'm going to call this one x for the inverse function. Let's make this blue, actually. So for x and y, everything's going to swap. My y values become my x values, and my x values become my y values. That's the whole point of kind of doing what we're doing, right? And then negative 3, this should be a negative 2, negative 2, negative 1, 0, 1, 2, and 3. And then you plot those points. Here's 1, 0. Here's 2, 1, and 2, negative 1. Here's 5, negative 2, and 5, 2. 10, negative 3, and 10, 3. There you go. And like I said, you can tilt your head to the right. If you know how to reflect these across, these points right here match up in that sense. Now, this This function is not one-to-one because its inverse is not also a function. But you can see what's going on there. Kind of sweet. Love looking at those inverses. Love the reflection stuff. Okay, 21. A and B. They're both word problems here. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius in feet of the outer ripple is r of t equals 0.6 t, where t is the time in seconds after the pebble strikes the water. The area of the circle is a of r equals pi r squared. Find and interpret a of r of t. So what's going on is you have a pond right here, and you drop a rock in there. Let's say I dropped it right there. Okay, and then you get this ripple effect, this thing where concentric circles start to form out. Now, concentric circles just mean circles with the same center but different radii. Obviously, those weren't perfect-looking circles. But the outer ripple, the very first one that was growing out here, was growing at this certain rate. T is the time in seconds and 0.6 t, radius is in feet. So this number, this 0.6, is 0.6 feet per 1 second. Every 1 second, the radius grows another 3/5 of a foot, which I don't know how many inches that is, but 3/5 of a foot there. So I'm just interpreting the problem. I'm just trying to help you out with what this problem is saying. So if time was 2 seconds, it would be 1.2. If it was 10 seconds, the ripple would have gone out to 6 feet. Actually seems a little slow now that I think about it. But yeah, so after 10 seconds, it does that, and it looks like it just keeps going. And there's probably a domain restriction. Eventually, you'll reach the end of the pond here, or it just dissipates and you can't see the ripple, but that's okay. So that outermost ripple there is growing at that rate. And they said the area of the circle is pi r squared, which is as area normally is. And they say find and interpret a of r of t. So a of r of t is just saying that I can find the area just by substituting in time. Let me kind of show you what I mean here. We're going to take a of r of t, which is pi r squared, which is 0.36 times pi t squared, like so. Okay? So that is a of r of t, once again. What that interpretation is there is no radius found in this formula anymore. We found a formula skipping right by radius. Okay? You are doing something outside with your friends, and you found out this rate. You did this formula, and you said, hey, guys, I can use a stopwatch and tell you how big the area of the circle is after some time. And if the time was 10 seconds, you could say that the area of the circle based on that radius grew to whatever this was, 10 squared, it would actually be 36 pi. But that's based on knowing how big the radius would be in that set. So I'm skipping right by knowing radius to go into that, and that's what the interpretation is. Again, a function of a function there is, that composition of functions is making that happen. 21b, the weekly cost of producing X units in a manufacturing process is C of X equals 60 plus 750. The number of units produced in T hours is X of T equals 50 T. Find and interpret C of X of T. Okay, cost, I assume the cost is in dollars right here. If I produce a certain number of units, I'm spending $60 per every unit that I make, plus an upfront cost for that week, which is going to be $750 for whatever reason. Maybe the employees that you pay or the machinery and whatever it is, but 60 per unit. But now I'm going to take C of X of T. This is going to be C of 50 T. Now what this thing said, well, I'll interpret it in a second. Let's first solve it. So this is 60 times 50 T plus 750, equals 3,000 T plus 750. Okay, this thing says you can figure out how much you are going to spend within that week based on how many hours you work. So so you can produce 50 units per hour is what this thing is saying here. So if we produce 50 units per hour and we multiply by the number of hours, then you can actually determine its cost straight up with this formula without actually even determining how many units you produced. You just say, hey, I worked 2 hours, therefore this is how much we spent for that. Part B, use a graphing utility to graph the cost as a function of time. Use the trace feature to estimate to 2 decimal places the time that must elapse until the cost increases to $15,000. So what we're going to do is we're going to make 2 different graphs here. We'll only use this function here. We can skip this one completely and just talk about this cost as a function of time, c of x of t. And we're going to graph that one for a y equals equation in our graphing calculator. And then there's another one right here. So this is y equals that. And then we have another one of y equals 15,000. We have to find out where these 2 things intersect right here. That's the idea. What value of t gives you $15,000, the same value for y out? Cha. Okay, I'll do 3,000. Now I can't use t. I kind of have to use the variable x here. It's no problem. Still means the same thing. It's our independent variable. And then I have 15,000. And we're going to use the intersect feature. Now for here, we definitely need to be able to find something where y equals 15,000. So I do need my y range to go up to there for sure. The x range looks like it's going to jump up very quickly here. 3,000x, that's your slope. I don't need my x to go even as large as this. I could probably just go up to like 7, and you'll be able to see what's there. Now my domain really should be greater than or equal to 0. My range is actually greater than or equal to 750. But no matter, I'll start at the origin here, and let's go up to probably 16,000 so you can at least see the point. Now when I go to the graph here, you'll see 2 different graphs. 1, 2. The first graph represents the slope, represents the cost given a certain amount of hours that this manufacturing facility works at. After 1 hour, this is how much you spend. 2 hours, this is how much you spend. We have to find out how many hours it takes to spend 15,000. And don't assume that it lands on an integer. It does say estimate to 2 decimal places where this intersects. So there's a trace feature here. Second, trace. Let's actually just use the calc button there. Intersect. We're going to find out where these 2 things intersect right here. First curve, second curve, and guess, and they intersect right at that point where x equals t equals 4.75. So t equals 4.75. That means 4.75 hours. You have a word problem, please answer it with a sentence or with units there. After 4.75 hours, which if you want to be very specific, it's 4 3/4 hours, which is 4 hours, 45 minutes. And I don't know if they can estimate that stuff always perfectly down to that exact amount. Hey, it's 45 minutes. We spent 15,000. Hooray. Which is actually a bad thing. That's a lot of money. You assume, however, that they make a lot of money selling these things. So whatever this thing is in this manufacturing process. So that's how long it would take for the cost to increase to 15,000. And again, you found out where those 2 things intersected. You could solve it algebraically as well. You set 15,000 equal to 3,000t plus 750. And that would, I don't know what 750, 14250. And then you divide by 3,000 and you'll get apparently 4.75 the same way. You can just confirm that algebraically, but solving it graphically also works. And that is 2 decimal places. There is something that's actually called the trace feature though, and it looks like this. You hit the trace button and all it lets you do is actually go along your graph like this until you find as good of a point as you can. Now ideally for this kind of problem, you'd actually want to zoom in on this point. So as I keep zooming in, then I can see it more and more. That's probably the one they're asking you to really do. But it's much better if we find the exact point of intersection because the graphing calculator can do that. So you can see as I keep zooming in, and now I use trace, you can see how I can get really close to 4.75 that same way. So that's just another means of doing it. However, once again, better to just be as accurate as possible. Okay, number 22, use the function f of x equals 10 minus the square root of 3 minus x to simplify this following. This is called a difference quotient here. Besides the term itself, you're still just evaluating this at a certain place where you fill in this f of x here, and then you subtract f of 2. This is 10 minus 3 minus 2 right there, all over x minus 2. So this becomes 10 minus the square root of 3 minus x minus, in here, this is 10 minus the square root of 1. So 10 minus 9, excuse me, 10 minus 1 is 9. So this is minus 9 right here, all over x minus 2. 10 minus 9 is 1. We get 1 minus the square root of 3 minus x all over x minus 2. Right there. And that's the most it simplifies to. And not too much to think about what this thing means at this moment, but the fact that we could simplify that. If there's anything to factor and cancel, you would go ahead and do that as well. Doesn't look like we can do anything else with that problem. Number 23, sketch the graph of this piecewise function here. 3x plus 7 is on the top when x is less than or equal to negative 3, and 4x squared minus 1 when x is greater than negative 3. So negative 3 is this big threshold where I decide to stop graphing one and start graphing the other. This one right here. And I'll go ahead and graph 3x plus 7 on one side. Now in order to do that, it's actually a lot easier if I do use its y-intercept of positive 7 right there, and go down 3 over 1 until I kind of find that side of the piecewise function. Now negative 3 is also included for this one, so I make sure that this is going to be a closed dot right here. These points are irrelevant because these are not values of x that are less than or equal to negative 3. And my graph in the end will look, at least for this part, like this. Okay, so it does go forever in the negative direction over here on this side of it. On the other side of it, we're going to figure out what the graph looks like. And actually, I don't think this graph is going to end up looking very tall. Too tall to the extent that I can't actually find that top point. But I start at 0, negative 1, and this is a stretch factor of 4. So if I go over 1, I'm going up 4 times 1, the 1 squared. Over 2, up 4 times 2 squared. You can see I'm already going up 16 at this point. It's way up here. So same with this side. You reflect across your axis of symmetry. You get way up there. I can't even find that other point right there. Let's see if I can move this thing a little bit, shift it a little bit downward for you, and actually find that other point a little better so I can at least talk about the open dot. So let's say that I can fit, I'm going to go ahead and plot those other points again. Let's see. About right there for 2 and negative 2, and about 3 and negative 3. Let's just say it goes very high up. Let's just say that it's this one here and that one there. Okay, but this one's an open circle here because it doesn't include negative 3. Whoops. You get the gist of this picture there. That's a parabola. And it goes forever on the direction here to the right. But if I zoom out here, I didn't zoom out very much, but you can see what it is that we're looking at. Okay, this piecewise function right here. It goes downward forever that way and to the left. Right here it starts anew. It does not include that point. It includes this one, and then it goes down and up like so. Okay, so there's the piecewise function. That was not a great looking one to graph on because it goes so high up. I wonder how high up that actually goes. Substitute negative 3 into here, 9 times 30. So it would go up to 35. This is a y value of 35, way up there. Obviously, like I said, not good for this graph. Okay, this last problem, increasing, decreasing, and constant. It's not asking is it increasing, decreasing, or constant. It's asking upon which intervals it's actually occurring at. And these are open intervals. In other words, these points I shouldn't actually be including, but these are relative maxes or mins or just places where it's changing form. So, and assume this was going all the way to the left there. I know you might think that it just started or ended there. Let's say it didn't. So this thing's increasing upon this interval here, all the way from negative infinity until this value, whatever that one is. So it's increasing. Let's use interval notation here. We're going from negative infinity all the way to 1, 2, 3, 4, 5, 6, negative 7, right there. There's actually another point where it increases. Once it hits down here, it goes back up. At this relative minimum, it begins to increase again from negative 1, and assume it increases the rest of the way because that's all you can see on your graph there. So to positive infinity. Notice how he's parentheses on -7 and -1 because at these exact points it's not actually increasing anymore, or it didn't just actually increase. It begins increasing thereafter. That's why I'm considering these as open circles. We won't put anything for those ones. Okay, decreasing. Oh, that's constant. Decreasing, it's only right there. And that's going to be from -3 to -1. Not including -3 or -1 for the same reason I mentioned for increasing. Final one's constant. And I almost do want to put closed interval there, meaning including those ones, but I guess we're not certain what it's doing at those points. Let's just say we don't know. It went from increasing to constant or constant to decreasing. So it's going from -7 to -3 right there. And we included the entire domain from negative infinity to positive infinity, except for these relative mins and maxes, those points where it changes actual form. That's it. Fiend!